Hello, welcome to this IChemE Global Awards 2021 webinar. My name is Matt Stalker and I'm your host for today's presentations. The IChemE Global Awards celebrate chemical, process and biochemical engineering excellence and are widely considered as the world's most prestigious chemical engineering awards. Today we'll be revealing the winner of the IChemE Energy Award, sponsored by the Chemical Engineer. This award recognises the best project, process or product to demonstrate excellence in efficient energy use or the development of energy production methods that reduce energy intensity. Our awards judging panel has been hard at work to review and rank all of the entries, and here are our finalists. We have a joint entry from Future Bay and Otto Simon, a joint entry from Panonia Bio, Energy Integration and Pillar Blowers and Compressors, a joint entry from Progressive Energy, SR, Kent and Johnson Matthey, and finally 3 entries from Saudi Aramco. 5 of our finalists are joining us today to tell us more about their work and to answer your questions. You can get in touch at any point during the webinar using the GoToWebinar questions box on screen. So let's get started with our first presentation. Representing Saudi Aramco, please welcome Abdullah Alaskar and Abdullah Al-Hamoud.
Hello.
Hi Abdullah, we can hear you. We can't see your screen yet, but we can hear you.
You can see my screen?
Not yet, no.
I tried to select the screen sharing, but I'm not sure what's happening, to be honest. I'm sorry.
That's okay. I'm just going to take back making myself presenter, and then I'll pass it back to you.
Okay.
And then a pop-up will come up again. And you feel free to talk me through what you're seeing. That's it. Thank you. We can see your screen now.
Great. Sorry about that. Good afternoon. My name is Abdullah Alaskar. I'm a Senior Operations Advisor, and I'm accompanied by my colleague Abdullah Al-Hamoud, who is a Process Engineer. We both work at North Ghawar Producing Department of Aramco. It is really our pleasure and honor to be here today with all of you and to be selected as finalists in the IChemE Global Energy Awards. Before we proceed, I just want to highlight that this project was a success because of a great team collaboration and hard work among 8 people from different departments within Aramco. The team, including myself and Abdullah, are Mohammed Al-Huraifi, Mohammed Al-Hajri, Abdullah Ghazal, Yopeng, Miguel Lopez, and Ramzi White. Starting with the objective of our project. As part of our department's energy program and our continuous efforts to enhance energy performance, we have developed a smart model to optimize the operation of my department's gas and oil separation plants. The aim of the model is to optimally distribute the feed across the plants, maximizing asset utilization while minimizing energy consumption. This slide shows a simplified schematic diagram of a typical GASP at my department. I would like to emphasize that most of the power consumed in my department is by the high pressure gas compressors and the water injection pumps. It is noteworthy to mention that all GASPs are not alike. Some GASPs are sharing gas compression, while others are sharing water handling train, and this was taken care of in our model. To put our project into perspective, the objective function was, as I mentioned earlier, the power consumption. As for the boundaries, we have the oil demand, which is the production target that we need to meet in that specific month. We also have the equipment min and max capacities per processing unit. And to comply with the reservoir strategy, we are setting the total capability of oil wells as a boundary. Our last boundary is related to system pressure profile. This is to ensure that the separated fluids are leaving the gas at the required pressure level. As for the controllable variables, we have the rate of each well group. Also, we have transfer lines as a controllable variables. This gives us the privilege of looking at the optimization from an overall network perspective. Finally, the last controllable variable is the number of running equipment. This slide shows the followed methodology in developing the model as part of our project. The first thing that was done was evaluating the different technologies, and in this project, GPROMS was selected. After that, the required data, both fluid and equipment-related data, was collected, and the physical-based model was constructed. The model was validated against real data. After that, the optimization problem was formulated and multiple scenarios were run. Now, I'll turn it over to my colleague, Abdullah Al-Hamoud, who will continue with you in the next part.
Thank you very much, Abdullah, for this. So I'll take it from here. So moving to an example, which is the simulation run that we have here. As we can see in this slide, this is how we could visually view the results of the optimization platform. So at the low demand case, there is a chance to shut down one gas or more for more optimization. And in this case, or in this slide, we can see that plant B is recommended to be shut down. So the rates of operating GASPs are adjusted, taking into account the gas capacity, as well as the available production from the oil wells. And on top of that, the swing production is directed to the gas such that the least power consumption can be attained in that case. This chart shows the average power consumption in megawatt hour versus the operating rate. 18 scenarios were run using the optimization platform, and each point represents the least energy consumption required to produce a certain target at a certain condition. As you can see here, the topmost curve shows the daily power required, the daily power consumption when all the plants are running. And the power consumption calculations were based on the calibrated results of the model. And moving down, you can see similar curves, assuming the shutdown of one plant for more power optimization. As we shut down gas, you notice that the curve does not extend at higher rates. As more gas are closed, the maximum producible rate of operating gas will be limited. And finally, through this new approach to optimize our operations and our number of running plants and gas, we were able to reduce the power consumption at our facility and our department. We were able to reduce flaring and emissions since the facilities are down. And finally, we were able to optimize the department operational cost since no chemicals are being consumed as the facility is down. That's all we have for you today, and thank you again for this chance to present our work for IChemE.
Okay, thank you very much. So it is now time for questions. And if you'd like to know more about our first presentation, now is the time to get in touch via the questions box. And while we give you a moment on that, don't forget there are more IChemE Award webinars coming up throughout the next fortnight. You can find all of the dates and times by visiting our website. That's icheme.org/global awards. Okay, we don't appear to have any questions, so we're going to move on. Thank you very much, Abdullah and Abdullah. We're now going to move on to our joint entry from Future Bay and Otto Simon. Please welcome Adrian Hutchings.
Good morning. Let me share my screen. Is my screen showing?
Yes, it is. Yes, it is, Adrian.
Excellent. Well, thank you very much for letting us speak today and putting us in as a finalist. We're really appreciative of that. Future Bay is a small technology development company, and we've partnered with Otto Simon to take our novel thermal cycle for energy storage and build the first unit and start designing the major units that we hope to install. So we're trying to drive forward a move towards the net zero future and a low carbon future. And we see that there are a number of issues that we can address. I think there's very more out there as well, but the ones we believe we can address are the intermittent and variable renewable generation, where really you've got to have energy storage to be able to move to a net zero renewable energy future. Even with the energy crisis that we've seen over the past few weeks, we're still in this country curtailing wind generation. We're still paying people to turn off wind turbines because it's coming at the wrong time. There's the very famous duck curve of energy consumption in California, where the energy is predominantly produced during the day from solar. They actually have an excess of it. And then as the sun goes down and air conditioning is required, there is a huge peak on the grid and they have to turn on other generation forms. At the moment, battery storage is out there and is doing a good job, but there are issues that I think we all understand with batteries in terms of cost, in terms of life, in terms of long duration. In fact, we're part of the BEIS long storage competition at the moment, and batteries weren't included in that due to the issues with doing long duration. The next area we're looking to address is cooling, and this is a real bugbear of mine. I was reading the International Energy Agency's report on the future of cooling, and it's very sobering. It's quite frightening, really. You know, we're looking at the moment of between 10 to 15% of the world's energy being used for cooling. And what comes out of the back of a cooling system is heat. And we're seeing some cities at night, the temperature in the city is raising by 1 or 2 degrees because of the heat being dissipated from air conditioning systems. And the IEA are saying that over the next 30 years, the increase is going to be phenomenal as more countries look to install air conditioning. In fact, they're seeing it growing from the 1.6 billion units out there today to 5.6 billion units by 2050. I mean, that frighteningly means 10 new air conditioning systems sold every second for the next 30 years. And all of those are using energy and putting out heat. And we believe we can certainly make a big inroad into that and actually reduce the amount of electricity that's being used. So we see our system very much in the energy storage and cooling sector, but it has other benefits. We can take in waste heat, and even very, very low grade waste heat that some people wouldn't even classify. So we can take heat down to 50 degrees C, store it, convert it into electricity to be used when required. And there is also the drive for decarbonisation of heating, and a byproduct of our system is the cooling and the heating. So those are the areas that we're looking to address. We don't need to address all of them for a system. You know, we can do energy storage and cooling, but if there are other needs, we deliver these additional benefits as well. So let me take you through what the system looks like. We've been working with Otto Simon, who have been our design and principal engineers on this. They've done a great job for us. They have worked with us in designing and building the first system, which has been installed. We're looking at delivering long duration energy storage, cooling, waste heat to power, and heating in a single system. So all those other systems that you saw, we can replace with a single, relatively low cost system. We're even just for the energy storage, we are a lower first cost and a lot lower life cycle cost than battery systems, because our storage medium is water, and water tanks are plentiful. We understand how to store water very well, and we can not only store energy and deliver it when it's used, but we can reduce the consumption of cooling systems significantly and of heating systems, and we can take in the waste heat. Because we're using water, it's a very benign system. It's based on industry available standard refrigeration equipment. It's non-toxic. We don't have any environmental impact. So we believe that this system has massive benefits, and we're looking very excited about moving it forward. How does it work? Well, this is the thermodynamic cycle. There are 2 patent families covering this now that FutureBay have registered. They cover about well over 100 inventive claims within those 2 patent families, and those patents have now been granted across countries across the world. So we have global protection for this, and it's actually a pretty straightforward system. What we have in the center is a standard industrial heat pump. For our first demonstrator, we utilized a heat pump that is normally used to produce ice for ice rinks. This system here is energized when you have renewable or off-peak or low-cost clean electricity. And as with any heat pump, it moves heat from one side to the other. So it produces a tank of hot water and a tank of cold water. And the way I like to look at this is that the cold side isn't as cold as your freezer, and the hot side isn't as hot as your kettle. So no extremes of temperature, no extremes of pressure, no exotic materials. Once you have your cold store, let's look at the hot side first, because this is a fairly standard organic Rankine cycle, which is a heat pump is a reverse Rankine cycle. So these again are fairly common pieces of equipment. For our first demonstrator, we used systems that are built and sold to farms to process biomass. And when you need electricity to being delivered, you drive the Rankine cycle, taking the heat as your evaporator on this side of the cycle, creating a vapor that drives a turbine that is then condensed with whatever it is you're looking to warm. Now this can be just ambient, and that could go either to space heating or domestic hot water, or could be discharged at ambient, but at a lower temperature than you normally would. So you can provide your heating and your electricity at any time that you desire. This is totally separate from the cold side, so these 2 systems do not have to operate at the same time. On this side, what we're doing is we're using ambient or something that you wish to cool as our evaporator, using that to evaporate the working fluid and drive the turbine producing electricity, and then using the cold store as the condenser to take that back to a liquid. So here you could very easily be providing air conditioning, refrigeration, or other cooling effects. So that's how the system works. You can envisage how this could be operated in a range of different industries. So for example, let's envisage that we have a hospital that's connected to a dodgy grid out somewhere where it's hot. You're going to need to have good reliable power. So you could drive our heat pump from solar PV or other energy sources and provide 24/7 reliable power. But if it's hot, you're also going to need to provide air conditioning. So there comes your air conditioning from our cold side. And you can have lots of domestic hot water for sterilization and washing. And if, for example, the hospital has a biomass furnace, we can take that waste heat and use that as well. So that would cover all the bases for us. But you could envisage somewhere like a hotel that in the morning people are wanting to shower, so they need the hot water, and there's a peak on the electricity demand, so you'd run the hot side only. And then in the afternoon, people come back from work or from holidays or wherever they've been, and the air conditioning is still required. There's a peak load onto the network again, and we can run our cold side. The system is highly scalable. These are pictures of the first unit that we built. Here's the heat pump that I was mentioning about that was from an ice rink, and here are the organic Rankine cycles. So that's a small unit producing tens of kilowatts of electricity and megawatt hours of cooling and heating capability. But with AutoSimon, we've looked at a range from the previous picture I showed you that is suitable as a single unit to multiple units that we're talking to BEIS for their long duration energy storage, where we're looking at megawatts of electricity from modules being utilized together. And this system showed here, you could look at using for large scale cold warehousing, data centers that produce a lot of heat, or attaching it to power plants for smoothing out those issues. So this is the system that we built. It was commissioned by Electricity Northwest Limited, who are a large distributed network operator in the UK. It was built under what's called a National Innovation Allowance, an NIA. AutoSimon acted as our principal designer, our project manager, our procurement. They did a lot of all the really detailed work for us, and they built this really, really well. So we were delighted with the partnership that we have with them. And this instrument was installed up at data center and was built to act on the back of a data center, taking the waste heat that is produced from the cooling systems and turning that into stored electricity that can be then utilized. We have a slide on AutoSimon, which I won't speak to the detail. What I will say though, they're a highly skilled and professional group, but I'd expect that. What I've found that I've been delighted with is the level of communication we have with them, both reactive and proactive. They will call us if there's an issue to be dealt with. We've worked extremely well, and we see them as part of our team. I think the thing that I've been really, really pleased about is they have the same level of passion and belief in the importance of this technology and this innovation that we do. And they believe that it can deliver real good into the world and heading towards net zero as we go forward. So it's been really good to work with them, and we're looking forward to working with them further on the next projects that we're looking now to go out and do larger projects for people. So if anybody's got some ideas of projects, we're happy to talk to you. And as I said, it was very successful, the project we did with them. This is some extracts from the report that Electricity Northwest produced for Ofgem. It showed that the technology could reduce net electricity consumption as it produced electricity from heat that would have been wasted. It reduced CO2 emissions by the net reduction in electricity consumption, the shifting electricity loads to lower CO2 nighttime electricity, and it reduces peaks on the network by shifting electrical loads to off-peak and by producing electricity during peak demand. We were able to, in this particular application, reduce the amount of energy required to produce the air conditioning by up to 50% in some circumstances, which was fantastic. And because we're shifting their air conditioning load to off-peak, and then we're producing electricity at the time they would have been using that electricity, we actually reduced the peak on the network for them by 150%, which is again pretty fantastic. A very quick run through of FutureBay and our operations with AutoSimon, and look forward to any questions you may have.
Okay, thank you very much, Adrian. So once again, it is time for questions. If you'd like to get in touch, please do so through the questions box. We've got our first question. You've obviously shared on screen some of what has been reported to Ofgem. What else did you actually learn from the Oldham application in terms of the technology and what you do going forward?
I think there were a number of things that we weren't quite sure about through all the theoretical modeling. One of the things that we needed to do was we needed to make sure there was stratification in the hot tank so that the heat didn't mix, and we built some separators on the advice of Otto Simon, and we used thermal cameras that proved that we could get the effective stratification in the tank that we required. The other one was we actually use phase change in the cold tank. We actually produce ice in a storage medium, and the storage of ice can be quite expensive. So we came up with our own solution, which I'm not going to share the details of at this stage, but that was very low cost and very, very effective. So the storage medium were the two areas where we needed to make sure we had our understanding correct. Because we're using effectively off-the-shelf equipment, yes, it does need tweaking, it does need honing for our need, but we expected those to work as they worked.
Okay, thank you. Next question, if you are able to share this, what kind of fluid is it that could take the temperature of 50 degrees that could drive the turbine?
We're using water, so it is stored in water. We store between 50 and 70 degrees. The working fluid is a refrigerant in the organic Rankine cycles, but it has it's a very benign. It has no global warming. It's one of the new synthetic refrigerants. So we're using water as our storage medium on both sides of the system.
Okay, and in terms of scale, what sort of range of scales do you think this technology can be practically used?
I don't think we'd go lower than tens of kilowatts. I think a single module sweet spot is in the 200 to 300 kilowatt of electrical output, but we see no reason we can do Rankine cycles, up to the sort of megawatt scale or multiples thereof for tens of megawatts. And it's certainly with a single tank, we can store 10 megawatt hours of electrical storage. And those are existing tanks, panel tanks that are used across the world.
Okay, thank you very much, Adrian. We're going to move on. So thank you for your presentation. It's time to meet our third finalist. Next up, representing the joint entry from Panonia Bio, Energy Integration and Pillar Blowers and Compressors. Please welcome Julian Power and Andras Volford.
Yeah, good morning, everyone. Could you see my screen?
Yes, we can, and we can hear you loud and clear.
Okay, that's fine. Could you see me also?
We can't see you. We can see your slides, including your future slides. You might need to switch your view if you're planning a different view.
Now it's okay?
That's better, yeah.
Okay. Okay, welcome everyone. Thank you for joining this talk, Decarbonizing and Electrifying Biorefineries to Produce Greener Bioethanol. So what were the aims for this project is distillation and dehydration are energy intense processes and account for a significant part of the energy consumption in the biorefineries. Smart heat integration and boosting energy efficiency of these areas are key to minimize production costs, minimize carbon emissions, and gain competitive advantage. After a detailed investigation of heat recovery opportunities, the design goals were defined such as 33 megawatts of natural gas was to be saved and a cost of 5.9 megawatts of electricity. The total capex for the project was 11.9 million, and the project is fully operational since March 2021. So these are the opportunities to recover energy. So we have 2 production lines. So we have, let's say, two rectifiers. So we start in the rectifier. Top of the rectifier, we have a ethanol in vapor phase. Then we send this to the condenser where we use cooling water. Then we get the alcohol in liquid phase. We send it to storage, and we pump it back as a liquid phase, of course, into the vaporizer, where we use some boiler steam. And then after that, we change the phase back into vapor phase to be able to feed the molecular sieve. And finally, to get the dehydrated product. So condensation and subsequent evaporation of rectified alcohol is a waste of energy. Cooling and reheating should be bypassed, but conditions of these 2 vapor streams don't match. Vapor compression is needed to increase the pressure and match the conditions. In addition, it is possible to utilize more energy to generate steam that otherwise is lost in the condensers. The generated steam can be used to supply heat to the evaporators and the distillation columns, further reducing boiler steam requirements. So this is the concept. We have, this is all the bypass. This is ethanol vapor from top of the rectifier at 340 millibars. This is the installed MBR series with the reboilers. We put 5.9 megawatts of electricity, and then we get the alcohol vapor at the right pressure and temperature to feed the molecular sieve. And also we condense some of the alcohol vapor to generate 16.6 tons per hour of steam, which is equivalent to 11.8 megawatts of natural gas. Significant reductions in steam consumption, cooling duty, the natural gas consumption, and we lower the OPEX and we reduce the greenhouse gas emissions. So we start from top of the rectifier at, as I mentioned before, 340 millibars. This is the phase equilibrium of alcohol, rectifier alcohol. So we don't want to be close to the gray line because that's the saturation curve. So we want to be in this region where we have a bit superheated alcohols. So we start compressing from top of the rectifier. This is first stage, second stage, third stage, and so on until we get to the stage number 7, MBR number 7, and MBR number 8. At this point, MBR number 7, we take out some alcohol, we send it to the reboiler, we condense the alcohol, and we generate steam. And in the final MBR number 8, we get the alcohol at the right conditions to feed directly to the molecular sieve and generate the dry vapors. This is the process flow diagram. Top of the rectifier, we have 2 lines. MBR line A is where we use the green colors, and MBR line B is where we use the blue colors. So we have a series of MBRs, 7 of them. We remove some alcohol in here to generate the steam, and then the remaining alcohol is sent directly to the molecular sieve. These are the reboiler. This is the trim condenser, and then we condense the alcohol. Is sent back to the column as a reflux, and this is where we get the steam to be able to send it to evaporators and the distillation columns. The conditions for that scene is 98 degrees. This is a process image. This is this side we have our rectifier A, and in the other side we have our rectifier B. This is all the MBRs. So we start from top of the rectifier. This is line B. Then these are the conditions, 334 millibars. One by one, we start increasing the pressure and the temperature of the alcohol. So at this point, we get nearly 500 millibars and so on until we get to the stage number 7, where we get close to the 3 bars. So the flow is split here between MBR 8 and the remaining alcohol is sent directly to the reboiler. So here in the MBR at the outlet of the MBR number 8, we get the 4 bars, and that has the right conditions to be sent to the molecular sieve. And this is all the reboilers where we condense the alcohol to be sent back to the column and also generate the steam. So our achievements: the energy efficiency of the bioethanol production has increased by using 33 megawatts less natural gas, reduced greenhouse gas emissions, avoiding the release of 6.75 tons per hour of carbon dioxide to the atmosphere, making our bioethanol even greener. Managed to make the operation of the plant stable despite the complexity of coupling multiple plant areas like the molecular sieve, the evaporators, the distillation columns, by process automations and program startup and sequences. Installed the first of its kind of development in a biorefinery in the world. And these are the patents that protect the process. And here are my contact details in case of any further questions or information. So now let's go to the Q&A session.
Okay, thank you very much, Julian. We'll give you a moment once again to add your questions into the questions box. First question: did the results match with your expectations?
Yes, indeed. That was the design, and I will leave these questions to one of the engineers who was working along with me, Andreas Wolford.
Thank you, Julian.
Okay.
Yes. So to answer the question 100%, it's of course there were challenges in the time of commissioning because there were no prior experience to start up such a system and to couple all these plant areas that Julian mentioned: distillation plant, evaporators, more sieves. But in terms of, we managed to troubleshoot all of these, and now the automation is such advanced that it's basically a matter of pushing buttons and the system starts up and stabilizes. So it's at the end we are really happy with the performance and the general savings and energy savings and performance is right there at the design spec.
Great, thank you very much. Next question: what would be the cost of MVR and what is the return on investment?
Yeah, well, the total capex for the project was 11.9 million euros, and the MVR's technology was in the level 3.5, below 3.5 and below 4 millions. That was the investment of the MVRs. 16 of them, I'm talking about the 16 of them. Because we installed two lines, so we installed 16 MVRs.
Okay, yes, that's my understanding. Thank you. We don't have any further questions, so we will move on. Thank you, Julian and Andras, for your input too. We're going to move on to our fourth finalist of the day, representing the joint entry from Progressive Energy, SR, Kent and Johnson Matthey. Please welcome Joe Ward.
Yes, good morning. Thank you very much. And thanks, first of all, to the IChemE for inviting us here this morning to present our project. It is an honour to be considered for the Energy Award today. I'm Joe Ward. I work with Progressive Energy, and I've been working on the low carbon hydrogen production plant, which is part of the HyNet Northwest project. Over the last 18 months, we've been working to develop a feed engineering and consenting package, and it's been developed under the BEIS Hydrogen Supply Programme. The programme is a UK government funded programme with the aim of developing commercial scale, high performance plants to deliver low carbon hydrogen, with the overarching objective of helping the country deliver net zero by 2050. The project has been developed by a team of over 100 people from the 4 companies shown on the right. It's been a huge effort by the entire team, and now I've got the challenge of squeezing all of this hard work into the next 5 minutes. The project aims to deliver material CO2 emissions for the northwest of England and for North Wales. But the hydrogen plant itself, which is the subject of today's presentation, is really just the centerpiece of the overall project. It's part of an overall HyNet Northwest decarbonisation cluster. So the hydrogen plant is shown in the middle of this map here, and it will be located at Stanlow Manufacturing Complex, which is also home to Stanlow Oil Refinery. HyNet Northwest, as I said, is a full cluster end to end. So it includes, after the plant, hydrogen distribution around the region, hydrogen storage and support with hydrogen use. Also CO2 capture, CO2 transport and storage to Liverpool Bay. HyNet Northwest, and specifically the low carbon hydrogen plant, has been sized based on the region's anticipated demand for hydrogen as we look to decarbonise the sectors around the region. We've sized the first plant based on initial demand in the area, and then over time that demand will grow, so we will have to build out further plants. Here we basically show a number of the major organisations looking to use HyNet's infrastructure to decarbonise sectors across the region, from cement to beer, domestic heat, etc. So the HyNet low carbon hydrogen plant is based around the Johnson Matthey low carbon hydrogen technology. The process at the core reforms natural gas and off gases from Stanlow Refinery to produce hydrogen, and it does this whilst capturing 97% of the total CO2 for permanent geological storage in Liverpool Bay. The technology is already recognised as a world-class technology option in the energy transition, and last year it won the IChemE award to recognise the potential of this technology. So what have we done in this? Sorry, apologies. So what have we done in this stage of development? So during the feed phase, the team which I mentioned earlier has further developed this core Johnson Matthey technology and built upon it to incorporate it into a full plant design. You can see the amount of work that's been undertaken here by looking at our full plant 3D model on the left-hand side and a more detailed shot of our carbon capture package on the right-hand side. What you'll notice is that the core technology is just one small piece of a total facility, and there's been a significant amount of work to make this a fully functional plant design. We'll step through some of the elements around the core technology now. So firstly, we require natural gas, and that is sourced from outside Stanlow manufacturing complex via a pipeline. The pipeline comes into the site. There's a second fuel, as I mentioned, which is refinery off gas, which comes from Stanlow refinery. These two fuels together are compressed and cleaned up and then sent over to the hydrogen plant. In addition to these gases, demineralized water is required by the process. This is produced in the utility area. We also produce fire water, cooling water, and wastewater treatment in this area. We have a cryogenic air separation unit, which produces pure oxygen, which is also required by the process's autothermal reformer. What you can see here is the core of the plant. In the foreground, you can see Johnson Matthey's low carbon hydrogen technology, and to the rear, our compressor house. This is absolutely integrated by design with the carbon capture package, which sits right next door. This is an amine-based system, and it removes CO2 from the syngas, which is then compressed and sent for storage. Hydrogen is purified, and then it is also sent both to Stanlow Refinery to decarbonize the refinery's operations and out to the Northwest region, as discussed before. Now, as I said, we need to grow this plant to meet the increasing demand as we drive towards net zero. So our layout has space to build a second phase quickly after the first, tripling the capacity of the overall hub. And here you can see the plant and how it fits within Stanlow manufacturing complex. So I understand that's been quite a rush through a very big project. I was asked to fit this into 5 minutes. So I hope that was a nice overview, but I obviously can't tell you everything. So we had a KT webinar a couple of weeks ago, and that was a couple of hours to quite a few people. That is all available online for anyone that is interested. And the question is, what's next? So the project is now progressing towards its final investment decision, with an aim of producing low carbon hydrogen as early as 2025 and scaling up over the next sort of 10 years to essentially replace 50% of the Northwest's natural gas consumption today is our ultimate goal on the drive towards net zero for the UK. Please feel free to check out our website. It's down the bottom, highnet.co.uk. There's lots of good sections on there, news and links to our social media. Both of these have the latest information. So thanks again to the IChemE. It's a real honour to be considered here for the 2021 Energy Award, alongside, as you've seen today, some fantastic projects from all around the globe. More than happy to answer any questions.
Okay, thank you very much, Joe. So we'll once again pause for your questions. Please type them into the questions box now. First question, there's been some criticism of generating hydrogen from methane. What are your thoughts on that?
I absolutely agree. There has been some criticism on producing hydrogen from methane. There are two ways of producing hydrogen at scale currently. So from methane with carbon capture and storage, and from renewable electricity using electrolyzers. Now, we as a project, as HyNet, see a space in the industry for both green and blue, and our infrastructure, hydrogen storage, transportation, distribution is sort of what we're calling colorblind. So green hydrogen, as and when it becomes available at scale, will be able to be built into the project. Blue hydrogen is seen as a transitional step, absolutely. But what we can do with blue hydrogen or hydrogen from methane in the short term is produce at scale, very quickly, large quantities of hydrogen, which is something we possibly don't have excess renewable energy and electrolyzer capacity to do quickly. So this is seen as a transitional step towards net zero, and our development goals and so on are driven by the CCC, the Climate Change Committee's recommendation for both blue and green hydrogen together, and also the government's hydrogen strategy. An important point for us is that we need to deliver low carbon hydrogen. That is the key. If we don't do that, we are not helping with the overall goal of reaching net zero. The government has recently announced its low carbon hydrogen standard, which is basically how do we prove that our hydrogen is genuinely low carbon and therefore helping towards climate change goals. We really support this, and this will be the method used to adjudicate our plant and to check that it is genuinely helping on the journey to net zero.
Okay, thank you very much. What criteria did you use to select the JM technology versus the alternative processes for producing blue hydrogen?
Okay, really good question. This was actually done before the feed phase, so this was done in the pre-feed phase over 18 months ago. The two most important parameters, if I could put it this way, thermal efficiency of the plant. So Johnson Matthey delivers over 85% thermal efficiency, and what that means is for a megawatt of natural gas entering the facility, 0.5 megawatts of hydrogen leave. So that's very important to produce as much hydrogen as we can from a fixed amount of natural gas feedstock. And the other one is carbon capture. So carbon capture, as I said before, is extremely important. If we build a plant that only captures 80% of the carbon dioxide, you'll see papers that say, well, we're really not helping anyone. The Johnson Matthey technology allows us to capture 97%. So of every carbon molecule coming in to the plant, 97% of those molecules leave as carbon dioxide down our transport and storage network for permanent geological storage. So those were the two selection criteria that really drove the decision to use Johnson Matthey's low carbon hydrogen technology.
Okay, thank you very much, Joe. We're going to move on. Thank you for your presentation. We now move on to our final presentation of the day, and it's back to Saudi Aramco. So please welcome Faisal Al-Quruni and Mohammed Al-Mahani.
Hello, everyone. We'll be sharing our screen.
Yes, you are. Yes.
Oh, can you see the screen yet?
Yes, we can.
Oh, perfect. Just let me put it in the presentation mode. So my colleague Mohammed Al-Mahani will be delivering the presentation. Mohammed, it's yours.
Good morning, ladies and gentlemen. Please allow me to start by introducing myself. My name is Mohammed Al-Mahani. I work in Saudi Aramco as energy coordinator of the largest oil field in the world. Today is my great pleasure to share with you a glimpse of our innovative energy management program that helped us to reduce our energy intensity. Energy efficiency is one of the major pillars that need to be considered seriously today more than ever to enhance life quality and to have a sustainable future. Therefore, we spared no effort to improve energy efficiency at our premises. In spite of all exerted efforts, strict policies, challenges, targets, and investment to achieve a continual improvement in energy efficiency, it would be hard to achieve best results without breakthrough solutions. Gasps are the first processing stage of crude oil after the extraction from wells, where it's separated into three products: oil, gas, and water. Oil and gas are then sent for further processing, while water is injected back to the reservoir by high-pressure injection pumps. Besides supplying the world with high-quality hydrocarbons, part of our responsibilities is to ensure that we minimize our emissions and enhance our energy efficiency. The key performance indicator used to gauge energy performance is energy intensity. For Saudi Aramco gasps, the energy intensity can be defined as the power consumption to the amount of useful product. The energy intensity formula excludes the produced water, since it's not a useful product, although it's one of the main gasp outputs, as we have seen in the previous slide, and it requires high energy to be injected back to the reservoir. As a result, a continuous improvement in energy intensity represented a major challenge to SGPD. However, we have implemented a very effective energy management program that facilitated a marvelous improvement in energy efficiency despite the highlighted challenges. As I mentioned, our energy management program has implemented many practices to reduce the energy intensity at our 14 gasps. Now I will walk you through the main optimization tools and initiatives in our energy management program. The first practice is Aramco invented patent, which is a mathematical algorithm using GAMS software that was developed along with a massive pipelines network called swing lines to divert crude oil from one facility to another in order to maximize equipment utilization at a certain facility and optimize the number of running equipment at an adjacent one. The mathematical algorithm supervised the operation of 14 facilities by reviewing process parameters and predicting the most energy efficiency mode of operation. Armed with this algorithm and swing lines, the energy intensity has been reduced beyond expectation by enhancing equipment energy efficiency at each gasp and reducing the number of operating equipment. The second one is also an Aramco invented patent to revive dead oil wells by an ejector. The motivation source of the ejector, or the high pressure source, is the pumped oil out of the gasp. On the other hand, the low pressure source is the dead well. Unlike the conventional old practice to revive oil wells through the high pressure test trap, the ejector eliminates flaring and hence maximize the production and reduce energy intensity. Despite the accomplished improvement from the highlighted practices, our energy management program has gone an extra mile by innovative third practice to maximize hydrocarbon production and minimize losses such as gas flaring to reduce energy intensity. This has also improved our energy performance and reduced our energy intensity. The last practice is the effective monitoring of the total power consumption in general and the significant energy users in particular, which has been accomplished by a dashboard that provides a real-time data of significant energy user performance to ensure that power consumption is being optimized by avoiding unnecessary equipment operation. The energy intensity improvement has been achieved in spite of the constant increase in the produced water, which represented a big challenge. This is partly because water is not part of GOSP energy intensity formula, and partly because of the increase in the high pressure injection pumps to accommodate the water increase. However, with the implemented practices, the challenges has been overcome. The success of the energy management program has led to improve the energy intensity at the southern part of the largest oil field in the world by 6.44% and 4% between 2018 and 19 and 2019 and 20 respectively. As you can see, we have continuous reduction on the energy intensity over the years. This is of a great importance to energy efficiency continuous improvement and to protect the environment. By this, I conclude the presentation. If you have any question, I'll be happy to answer.
Okay, thank you very much. So once again, we'll take a quick pause for questions. If you have a question, please type it into the questions box now. And while I give you a moment on that, if you've been suitably inspired by today's presentations, it might be time to start thinking about your own awards entry for next year. Keep an eye on the IChemE website for more information, but we plan to open for entries in early March 2022. We do have a question. What advice would you give to another organisation seeking to undertake a similar study?
Yes, this is Faisal Groni. Thank you for the question. So first of all, one of the tools that helped us identify this opportunity is using experienced organization. So we have done energy assessment that helped us do so. Also, training is always fruitful. Like our energy team here in the department has gone through a lot of international certificates that help them come up with such a practice. Also, like attending such seminars and conferences or awards will help you see other good practices as well. So this is what helped us this is the advice that we could give to others. Thank you.
Thank you. Next question. Did the company reduce the amount of gas to be flared?
Yeah, this is true. Through the system we have, flare gas recovery system. So our flared gas was recovered and produced. So this is one of the main things that we have done.
Okay, we'll leave it there. Thank you very much to both of you. We have reached the moment that we've all been waiting for. It's time to find out the winner of the IChemE Energy Award, sponsored by the chemical engineer. Before we do that, let me thank all of our finalists for joining us today and taking the time to tell us more about your work. Thank you very much indeed. So let's start by announcing our highly commended entries, and they are the joint entry from Future Bay and Otto Simon, and the joint entry from Progressive Energy, SR, Kent and Johnson Matthey. So well done and congratulations to everybody associated with those projects. But now it's time to announce the winner. So ladies and gentlemen, the winner of the IChemE Energy Award, sponsored by the chemical engineer, is the joint entry from Panonia Bio, Energy Integration and Pillar Blowers and Compressors. So congratulations to everybody who worked on our winning entry. Julian, Andras, I hope you're still with us. If we can get you back on screen or certainly on microphone, tell us, how does it feel to be an IChemE Award winner?
Hello, yes, we are still here. Well, this is such a great achievement, and it's not only to bring this to the company, but also to bring this to the chemical engineering, to the industry, so we can change the way we have seen the distillation columns to have even greener bioproducts. So we are so excited, and thank you everyone for this award. I'm so happy.
Good. Well, look, congratulations once again, and thank you for joining us, and to all of our finalists and everybody who's joined us for the webinar. We've still got plenty more IChemE Award webinars to come over the next 2 weeks. We're back this afternoon to announce the winner of our Diversity and Inclusion Award, but that is everything for now.
Matt, can I say?
Yeah.
I would like Andras. How do you feel now?
Oh, it's a real honor. Thank you so much, and I'd like to congratulate to all the other entries. We've seen some fantastic presentations today, so we're extremely honored that amongst these very strong entries, we were the selected ones. So thank you very much.
Well done once again from everybody at IChemE. That wraps up today's first award presentation. Hopefully we'll see you on another award presentation later on during this year's programme. But until then, thank you and goodbye.